How are you today? Today we're going to discuss first order nucleophilic substitution reactions, also known as SN1 reactions. Unlike the reaction that we've been previously discussing in our lectures, being the second order nucleophilic substitution, which are also known as SN2 reactions. So when tert butyl bromide is placed in boiling methanol, methyl tert butyl ether can be isolated from the reaction mixture. Because the reaction takes place with the solvent acting as a nucleophile, it is called solvosis. Solvo for solvent plus lysis meaning cleavage. And it's important to note that not all solvents act as nucleophiles in SN1 reactions. This is just one of the examples where the solvent is also a nucleophile. Methanol is a weak nucleophile because it's a neutral nucleophile. And tert butyl bromide is a hindered halide, therefore a poor SN2 substrate. Remember, SN2 substrates should be an unhindered, should not be highly hindered. And the best in this category of alkyl halides is the methyl halides, followed by the primary alkyl halides. So those are the most appropriate substrates for SN2 mechanisms because they are not hindered. But for tert butyl bromide, which is a tertiary alkyl halide, then it is a hindered halide and is a very poor SN2 substrate. And what it means is that, of course, this particular reaction cannot be proceeding via SN2 mechanism. An interesting characteristic of this reaction is that its rate does not also depend on the concentration of methanol, which is a nucleophile, but the rate depends only on the concentration of the starting material, the tert butyl bromide, which is the alkyl halide in this case, and also the substrate. So, of course, the alkyl halide is a substrate where the reaction is going to take place. And in this particular type of reaction, the rate depends only on the concentration of the substrate and not on the concentration of the nucleophile. But for SN2 reactions, the rate of reaction is dependent on the concentration of both the nucleophile and also the substrate. But for SN1, the rate is dependent on the concentration of only the substrate, which in this case is an alkyl halide. But you will see later that also you can have other substrates. So you can see it's dependent on the concentration of the alkyl halide, tert butyl tert butyl bromide. This rate is first order overall, first order in the concentration of the alkyl halide, which is the substrate, and zero order in the concentration of the nucleophile, which is methanol in this case. So as it is just the same as saying that the rate is the concentration of the nucleophile does not determine the rate of SN1 reactions. Because the rate does not depend on the concentration of the nucleophile, we infer that the nucleophile is not present in the transition state of the rate determining step. The nucleophile must react after the slow step. So the nucleophile reacts after the slow step, which is the rate determining step. So of course, in a multi-step reaction, the rate determining step is the slowest step. So this type of substitution is known as SN1 reaction for substitution, nucleophilic, and unimolecular, and it's because the rate is dependent on the concentration of only the alkyl halide and not the nucleophile. But for SN2, the rate is dependent on the concentration of the nucleophile plus the alkyl halide, which is the substrate. So generally, SN2 reactions are dependent. The rate is dependent on the concentration of the substrate and also the nucleophile. The term unimolecular means that there is only one molecule involved in the transition state of the rate determining step. We will see that later. The mechanism of SN1 reaction of tert butyl bromide with methanol is shown below. So again, this is a multi-step reaction, unlike the SN2 reaction, which is a concerted or one-step reaction. So ionization of the alkyl halide, which is the first step, is the slow step and the rate determining step. So this first step of ionization, or you can say the loss of the bromide, or if it was any other alkyl halide, the loss of the halide to form the carbocation is the first step. So formation of the carbocation is the rate determining step. So the formation of the carbocation is the rate determining step. So this is what happens. So you have the tert butyl bromide. So there will be this bromide. This bond will break, of course, and the 2 electrons of this covalent bond will move with the bromine to form a bromide. And also, because the 2 electrons have moved with the bromine, then the carbon will have a positive charge. So the electron that was donated by carbon and the one that was donated by bromine will both move with bromine atom, and they form a bromide ion. So that's the first step. So this step sometimes is referred to ionization. So this is the step which is referred to as ionization, because you can see carbon is going now to bear a positive charge or to form a carbocation. So this step can also be called ionization. So again, you can see this is a reverse reaction for the forward, and the backward reaction is more favored to form the alkyl halide, because of course it's neutral as compared to the formation of these 2 ions, that is the bromide and also the carbon bearing a positive charge, that's carbocation. But always remember, this is the rate determining step and it's the slowest step. And here you can see only the concentration of the alkyl halide or the substrate. And that's why, because it's a slowest step, this is the rate determining step, and it only involves the substrate, not the nucleophile. Step number 2, there is nucleophilic attack on the carbocation. So the nucleophile in this case we've indicated is methanol, which is a weak nucleophile. And we know that for SN2 reactions, they require strong nucleophiles. And that's why if you have this nucleophile, then there's no way it can undergo SN2 reactions or mechanism. But these weak nucleophiles can easily undergo SN1 mechanism, because they are reacting with a strong electrophile. So when you have a strong electrophile and when you have weak nucleophiles, they can easily react. But if you have a weak nucleophile and a weak nucleophile and a weak electrophile, then it's not possible for a reaction to proceed. So in this case, we have a strong electrophile because there is a complete positive charge. Then here we have a neutral molecule, which is a nucleophile, because it's going to use its lone pair of electrons to donate electrons. Strong nucleophiles usually have negative charges, but there are also some strong weak nucleophiles with negative charge. So when a lone pair of electrons is used to form a covalent bond with this carbocation or carbon which is bearing a positive charge, then you have a positive charge on oxygen, which is using a lone pair of electrons to form a new bond with carbon, which is lacking in electrons. So this is a new covalent bond, but we should have shown it. This should be blue, so that shows that the 2 electrons are these lone pair of electrons, which are forming a new bond with this carbon. So I'll change this. So they form, this is a very fast, a rapid reaction or a fast reaction. So this is not the rate determining step because it's a very fast reaction. The rate determining step is the slowest step. So this is not neutral. So the reaction still proceeds another step. The final step is the loss of a proton to the solvent so that it forms the ether. So again, how does that happen? So you have methanol, which is the solvent, and it's rich in electrons. It's a nucleophile, though it's weak, but it can abstract a proton from the protonated ether. And why is that easy? It's because when you have a positive charge on oxygen, initially, remember, you have there's oxygen, hydrogen. So of course this bond is polarized to some extent, even before it's when before the positive charge is on that oxygen, it's still polarized because of oxygen being more electronegative as compared to hydrogen. So this bond is polarized, and oxygen will bear some partial negative charge and hydrogen will have some partial positive charge, so it will be acidic. So, but when there will be new bond formed with electrophilic carbon, then oxygen becomes protonated. So this hydrogen now becomes highly acidic because these two electrons will tend to move towards the oxygen atom to neutralize the positive charge, making this proton more acidic as compared to when there was no positive charge. So when it becomes highly acidic, then it can easily, of course, it means also this bond is highly polarized when there's a positive charge, and through inductive effect, the two electrons will move comfortably to stabilize that positive charge, then leave this hydrogen with a positive charge, which can easily be picked by a lone pair of electrons on oxygen of this solvent molecule. And of course, when it is highly acidic, that's when it can easily be picked also by this base. Now it's known as a base. When there's a formation of an electron-rich species with a hydrogen, it's known as a base. But when it's forming a new bond using the lone pair of electrons, in this case, a particular case with a carbon which is bearing electrons positive charge, then it will be known as a nucleophile. So when that happens, what happens? It picks this hydrogen without the electron that was shared with this oxygen, leaving behind the two electrons, which will stabilize that positive charge. So you get back the lone pair of electrons, and then also the positive charge is neutralized. So you get your ether, and this is also a fast reaction. So it's not a rate determining step. And also you get ethanol, methanol protonated. So that is how the ether is synthesized. So the SN1 mechanism is a multi-step process. I've already indicated that. And the first step is a slow ionization to form a carbocation. So this is the energy diagram for SN1 reactions, and you can see it's a multi-step reaction as compared to SN2, which is a one-step reaction, one transition step, and of course, and the rate is dependent on the concentration of both the substrate and the nucleophile, because you can see at the transition state you have both of them. You have the nucleophile there, you have the substrate. So the bond is trying to form to the electrophilic carbon on the substrate, and the bond to the halogen is also trying to break at the transition state. That's why the rate of reaction of SN2 is dependent on both the nucleophile and the substrate. But let's see for SN1, because it's a multi-step reaction, there are some slow steps and there are some fast steps. So the first step to ionization to form a carbocation is a slow step. And you can see, so you have the substrate, you have the nucleophile. So the first step is where there is ionization, where the halide is going to be lost. The leaving group leaves and forms a halide and a carbocation. So this is the first step. So of course there's a transition step there, and finally it forms the carbocation and the halide. Then the nucleophile is there. So the next step is where the nucleophile is going to react with the carbocation. Then there's a transition step and finally forms the product. So this is a product. You have the alkyl part of the molecule, which was attached to the halogen, now forming a new bond with a new nucleophile, and the halide leaves as a leaving group. This other process you already understand. This is an energy diagram also of SN1. And here again, this is the alkyl halide, this is a nucleophile. And we've said the properties of SN2 are quite different from the properties of SN1. The first is that when you compare the two, for SN2, you need an unhindered substrate, one which is not hindered, like a methyl halide. That is the best for SN2. It's not hindered. And you also need a strong nucleophile. For SN1, you need a hindered Alkyl halide, that is a tertiary alkyl halide, is the best for SN1. And then you need a nucleophile, which is not really a strong nucleophile. So from there, we will next we will discuss about the substrate effects on SN1 reactions. Thank you.